Okay, hello everyone. Welcome again to the Multi-Agent Learning Seminar. Today we're really excited to have Siqi Liu with us. Siqi is a staff research engineer at Google DeepMind and also a final year PhD student at UCL. He's supervised by David Silver and Nicolas Heess. His research sits at the intersection of game theory, robotics, deep RL, with a particular interest in scaling principled game-theoretic methods to real-world games. We're really excited to have you, Siqi, and take it away when you're ready.
Thank you for the warm introduction, and thank you, Manfred and Rupali, for the invitation as well. It's an honor to have this opportunity to share some of our recent work with this audience. I'm on behalf I'm Siqi, and I'm going to present on behalf of my co-authors Luke, Georgios, Ian, and Nicholas. So the focus of this work is on representation learning of normal form games. And just to set the stage, I'm sure this audience, this is not new. So what is normal form games? Normal form games are basically the simplest and the most foundational object in game theory that represents strategic interactions between players. These could be competitive or cooperative interactions or general sum interactions, and a game could be between two players or more players. So the prototypical example I usually gave would be just the rock paper scissors game. Here you have two players; they have 3 actions each, and usually these games are written as in this matrix form, where we write out basically the utility received by each player when they play that specific joint actions. And you can imagine with more than 2 players, you need to be working with a payoff tensor instead of a matrix. Now, this is a pretty restrictive game formulation, and you might ask, rightfully so, should we still care about this kind of game formulation, given especially in the age of LLMs these days? It turns out that with all the power of LLMs today, the best way to evaluate them is still subjecting them to play this normal form game. So this is an example of how the game is typically played. So basically on the web, anyone can go to the LLM Arena website and where they can prompt a pair of models that are sampled randomly that are with hidden identity. And they can prompt the 2 models and observe their responses. At the end of it, they can decide which player win or lost in this round. And all of these responses are then collated into this tabular form. So here, again, if you just squint at this, you can see that this is actually just a 2-player zero-sum game where you can see the pairwise win rate between any pair of models. And now a useful question to ask then is, given these pairwise win rates between all of these models, what would be a useful ranking that we can derive from it? And here, a pretty popular option would be that of ELO. So ELO was a rating measure that was developed initially for chess and Go, but also now used in tennis. And with the ELO ratings, basically have this pretty simple formula. And in some sense, you can think of ELO as a representation learning of normal form game already, specifically for 2-player zero-sum games. Because if you given all the ELO ranking, you're supposed to be able to recover all the pairwise win rates on the right-hand side just by plugging the rating into the formula. If you have a rating for player B and player A, then you should be able to work out what should be the expected win rate in that pairwise interaction. Now, there are all sorts of limitations to ELO, and those are well documented in the ranking literature. But in some sense, this is already one form of representation learning that we can think of. Now, the other area where normal form games have been applied quite a bit are used in learning. So here, as an example, these are some visualization of the kind of algorithm that follow from fictitious play, double oracle, or PSRO. So all of these are, broadly speaking, kind of following the same basic idea, which is given a game, you kind of start off with some initial policy, and that's your initial set of policies. And what you then do is to best respond to some mixture over that initial set. And now the choice of that mixture is important. And the popular choice would be you would want to best respond to the Nash equilibrium over that set. And at every iteration, you'll introduce that best response back into the set. And the algorithm goes then this iterative approach would eventually lead to convergence to the Nash equilibrium of the full game. So you can imagine in this process, you're actually solving a sequence of normal form game again. But it's just that here you're using equilibrium solvers at every iteration. So here on the left, what I'm visualizing is the payoff matrix between 8 policies that are iteratively expanded in this way. And on the right, I'm basically showing the Nash equilibrium that is solved given the subgame. So here, the 3x3 matrix solving for this 3x3 payoff matrix will give you the 4th row, on the right-hand side, for example. And you can see this kind of iterative convergence going on. And it's important to know that this kind of idea, so this population of policy is actually not playing a normal form game under the hood. They're actually playing a sequential imperfect information game that is shown on the right. So here is basically 2-player playing this sequential version of rock, paper, scissors. So they need to run around and then pick up squares that correspond to rock, paper, scissors resources. So here you can see the blue player actually learned the strategy to actually wait around in the corner until it has noticed the right player is picking up one type of resource, and then it quickly go up and pick up the counter. So this is the kind of a strategic interaction you can see emerging in this type of algorithm, which leverage normal form game. So the question then is, and if you kind of zoom out and look at the field, you kind of see that starting from the same data modality of normal form game, people we kind of have this emergence of different sub-community that are focused on different specific topics in this area. So you have community forming around ranking and payoff prediction problems. There we see methods that extends from ELO, such as multidimensional ELO, X-ELO, Nash averaging, with all the benefit that come with those. But also you have on the other side equilibrium solving community, which is focused on solving for Nash equilibrium, correlated equilibrium, etc. So the question we want to address in this project is to ask, do we have a way to introduce a unified representation learning architecture that we can put in the middle, so that with this unified representation learning techniques, we can actually address a range of these problems downstream. So this pattern is kind of similar to kind of how the machine learning community tackled computer vision and natural language, where you think of pixels as the data modality and try to figure out what are the inherent property to that data modality. So here, the object of study is normal form games, and the property that we want to leverage is player action equivariance. So now the next step would be to take a look at normal form games as the data modality and what are the properties that we can actually leverage here. So the first observation I will make is that in the normal form games, in the typical way that we write them down in this table, in this matrix form, it is actually, if we were to permute actions or players in this game, we do not fundamentally change the game. You can imagine here we have written down rock, paper, scissors game, but equivalently, if I were to say writing down rock, scissors, paper, it would still be the same game. Nothing strategically would change. So the first intuition would be for this representation learning setup, the function class that we should target would be a equivariant embedding function that go from an input game tensor, input a payoff tensor, to a set of action embedding vectors. So from G to A here. Now, if let's say G is n player and T action each, then we'll basically have n times T action embedding vectors. And ideally, the property we would like would be if I were to swap the ordering of the columns of the actions or the players, then that kind of permutation would be reflected in the outputs too. So now it turns out this is not a new observation actually. So in the game theory literature, if we go back, we can see that there are well-known definition about of these kind of relationship, which are named under, which are referred to as strongly isomorphic games. So here again, for example, so here I'm showing two games, so coordination game and anti-coordination game. You would say they're kind of different, but you can imagine we can actually construct anti-coordination game by simply permuting the action, by simply permuting the columns or permuting the rows of the coordination game. So in that sense, these two games are said to be strongly isomorphic because we can construct one from the other through this kind of permutation operation. And if you think about it intuitively, they're actually also kind of equivalent in a sense, because every action is want to match up with one other action from the other player and want to avoid the other one. So in that sense, they're kind of similar. Now, we can make a stronger statement, which is if G and G prime coincide, we will say that the game is automorphic under a certain permutation. So here, for example, for the coordination game, again, if you think of if you permute both the row and the column, you'll recover the same game. So the coordination game is automorphic under that permutation. And strongly isomorphic games are strategically equivalent. So it turns out that if we combine, so we can go one step further. So in the paper, we kind of we propose this definition of strategically equivalent actions. So we say two actions are strategically equivalent if there exists a strong automorphism over the game, such that the two actions permutes. So if two actions permutes such that it does not change the game payoff, that means that they are strategically equivalent. And under this definition, and if the embedding function is equivariant to player and action permutation, then we have some nice properties. So for example, repeated action will guarantee to have identical action embeddings. And if you have symmetric players, they will by construction have identical sets of action embeddings. So these are some nice properties and that we will also see in the experiments. And these just pop out from the equivariance property of normal form games. Okay, any questions? Not, I will go to the model section. Okay, so yeah, maybe we can come back to this later if needed. So now the next question is then, what kind of function can we propose here? So as the name suggests, you would have guessed that it's kind of related to transformers. And in a sense it is. So just as a reminder, so in transformer, basically the fundamental operation is that of attention. So attention operation operates on Curie key values. And usually, so key and value are usually function of the same set of inputs. And Curie could be either different, a function of a different set of inputs, or a function of the same set of inputs. If they're the same, then the attention mechanism is referred to as the self-attention. If they're not, then that's the cross-attention mechanism. And a useful property here is to note is that the output from this attention operation is order invariant with respect to key values and equivariant with respect to queries. So if you were to swap the ordering of the queries, the output would also swap in that correspondingly. But if you were to change the ordering, permute the key value pairs, the output would not change. So this is kind of the fundamental building block that we leverage in the design of the architecture. Okay, so now what is the architecture that I'm talking about? So here's kind of the high-level overview. The basic idea is we would start off, the NfgTransformer is composed of a sequence of transformer blocks. And the overall network will basically take as input the payoff tensor. And at the beginning, it will basically initialize action embedding vectors. So here they're all zero initialized. They're zero initialized because we do not want the output to be the embedding of an action to depend on its ordering in which it appeared in the game, which will then ensure equivariance. So the action embeddings are zero initialized. They'll go through a sequence of k transformer blocks. And at the end of the case steps, we'll basically obtain a set of updated action embeddings. Okay. So what happens within each block? At the high level, within each block, we would like to update each action embedding. So to player P, the T's action to player P, it will be updated based on, it will be a function of the payoff value that action receives under every joint action it has been part of. So there's a question, do you use positional embedding architecture to get, so no, that's a really good question. So usually in natural language, you care about positional embedding because the positional information is important. Here, specifically, we want to avoid that. Because again, if you were to swap the position of the actions, that should not affect the action embedding. If you change if now rock appears last in the rock paper scissors game, the embedding of rock action should remain the same. So yes, so no, there's no position embedding. That's something that we actively avoid. Yeah. So to keep the order, to keep the information about player ordering. So the way we keep the ordering is by relying on more on the equivariance property with respect to queries. So as we will see, basically in the architecture, every time the query are always the action embeddings. So that's what kind of string them through together all the way, so that the output are kind of tied to the input through the sequence of queries. And we don't need to rely on position embeddings. Okay, so let's continue. Just feel free to jump in because the architecture is a bit complicated, but hopefully I'll go through them step by step and just let me know if anything's not clear. So as I said, as I was saying, so within each block, basically, we would like to update each action embedding based on the payoff it received under every joint action it has been part of, as well as the current set of action embeddings. That's kind of the basic gist of it. And in particular, that set of the functions operates over this set in the sense that we don't care about the ordering in which these joint action come in. So break it down further. Basically, this block contains 3 stages. The first stage would be action to joint action. So here, basically, we kind of take any joint action A. We would start off with a self-attention mechanism, which basically concatenate the payoff received by each player under this joint action, and then project that into a vector representation from the perspective of every player. So you could imagine this is like this is there's this joint action that I played in. This is how much I've got. This is how much everyone have got. I will look at everyone's this kind of action value information and kind of assimilate all that information in this vector representation. So this is what we refer to as a play. So this is a play of an action A1 under the joint action A. Okay. And the next step, and you can imagine that for the same action A1 here, it will participate, the same action will participate in many joint actions. So the next step would be to take that entire set. So basically for every APT, so for every single action, we will gather all the action it has been part of. Every joint action it has been part of. And that would be our key value set. And then the query will be the action embedding itself. So here is basically like for this action has played in all of these under these joint actions with the information that they have gathered from each of those joint action value, and assimilate all that information into an updated version of the action embedding. So that's the APT prime here. And then there's the final stage. So this is not strictly necessary, but empirically it does seem to help, especially in tasks like Nash equilibrium solving, where we basically allow this shortcut to pass information between action embeddings. So at this stage, the output would already be a set of action embedding that's been updated in one round, basically. And here, basically, there's a final self-attention layer where you could have every action embedding look at every other action that's present in the game and update your own embedding again. So these three stages will then translate to this figure, which is probably more complicated than what I just described. But essentially, they achieve the goal of assimilating information that's present in the payoff tensor via and assimilate all that information into the action embedding vectors. Okay, any questions? Okay, so I will, yeah, here.
Yeah. So why do you find the need to embed the games in the first place? So why do we have to go through all these steps? Where's the end purpose of it?
Do you mean why do we need to embed a payoff tensor?
This what do you expect to have at the end of the architecture?
Right. So yeah. Okay. So this here, what I'm proposing here, you can think of it as just the encoder. So this by itself doesn't do anything, right? This by itself just says, given a payoff tensor, now assimilate all that information into action embeddings. And then what would be useful, which I will show a bit later, would be that given this action embedding, this would actually allow you to ask all sorts of questions about the game. So for instance, and that would be at every granularity. So for instance, if you want to like predict payoff, you can then basically take some of these action embeddings and then train a decoder that would decode the expected payoff based on these action embeddings. Or say if you want to solve for Nash equilibrium, you can basically design the decoder in different ways, but this would be a unified way to encode the game into action embeddings. And also this done this way, the action embedding will be permutation equivariant. So if in the input game you were to swap rock and scissors, in the embedding space they will be swapped as well. Another question without non-linearity. So we can look kind of it could be. So actually, Luke, who is one of the co-authors, so the question is, without non-linearity, the mechanism looks kind of like computing CE or CCE for every permutation of players. So I'm not quite sure. I'm not an expert on CCE solving, but one of the co-author, Luke, he worked on this idea called neural equilibrium solving, which is kind of a specialized architecture designed for solving for CE and CCE. And we do have some comparison in terms of the performance. But here, yeah, I'm not quite certain as to how similar it would be. Yeah. So another comment. Sending this alternative ELO rating, so you probably know when I get this. Yeah. Okay. Yeah. So I do have some results on kind of comparison to ELO. It's kind of, I guess, not strictly, because this does require learning, does require training on some set of games. But I'll kind of show some results and we can maybe discuss some of the differences there. Okay, so that's the architecture. Basically, at this stage, we have gone from a payoff tensor to a set of action embedding vectors. And these embedding vectors will reflect permutations that happened in the game, which do not change the strategic interaction described by the game. So now we have these embedding vectors. And the question is, how do we put them back together in different forms to get to results that we like. So this is basically what we have done. We take a payoff tensor G, we pass that through the NfgTransformer, we get to these n times t action embedding vectors. And then we can do multiple things. I'm showing 3 here, but perhaps the most common one that people would want to do, given a game representation, would be to solve for, say, Nash equilibrium. So here, one way to do that would be to take each of these action embedding vectors and pass them through some linear layers or MLP that will basically project it into a logit. And then you can take the softmax over the logis. That will produce a marginal distribution over the action for each player. And then you can then evaluate just the exploitability or the exploitability of that set of marginal distribution based on the game. And that would be your loss function, for example. Another example would be payoff reconstruction. So here, for example, if you have access to these action embedding now, what you can then do is to just compose them into different joint actions for which you want to predict an outcome. And then that would then go through, for example, another self-attention layer, which will give you one output for every player for every joint action. Now, the output of that, again, you can train that by just minimizing L2 loss compared against the ground truth payoff tensor that you have as the input. In the middle, you have this is a similar task to the Nash solving, but this is, for example, to estimate the maximum deviation gain for every joint action. So you can imagine all the ones that get 0 maximum deviation gain would be a pure strategy Nash of the game. So this would be if you want to find all the pure strategy Nash of the game, this is kind of a loss function that you can minimize. Okay, so hopefully this clarify a bit why we want to go through this, and then what we can do downstream of this encoder stack that I was describing. Another comment: self-attention has cost of quadratic. They're Nash solver that are polynomial. The other is of the other is flash. Yes, so computation cost is a concern in the same way as all the other transformer architectures, and it is quadratic. So Nash solver, I think for 2-player zero-sum game would be an LP, and that would be tractable. But I think the comparison here is a bit, we're not maybe comparing the same thing, because in this transformer architecture, when we talk about computation costs, we're just talking about flops, and again, these here the same architecture should work for unpaired general sum, and all the experiments we run would be on unpaired general sum too. So these are also approximate solutions, not the exact ones. But yeah, that's a good comment. So computational cost will be a concern, and the slight nice thing about this is all the innovation in the transformer community would kind of carry through. So for example, like mixture of depths, that kind of stuff would carry through too. And flash attention, as you mentioned. Another question. Is actually a sequential over time if you want this. Maybe we can come back to this later. Just so we maybe get more context. I'll come back to the comments. Okay, so as I said, so these are the 3 tasks that we kind of experimented with in the paper. There could be probably other tasks we can use this for. And how are the results? Here we're basically evaluating this encoder-decoder architecture on a suite of basically games of different sizes. So 2-player 16 action each, 2-player 64 actions each, 3-player up to 3-player 16 action each. And these are basically sampled from a distribution of games where the equilibrium would be such that we can cover the full space of equilibrium. So these are not zero-sum games, or it doesn't have any specific structure built in to the distribution. So on the left, we're basically showing the Nash the explainability here, and basically the takeaway is the architecture do well, as you expect. And here the baseline is basically, so the baseline MLP, which would be a pretty dumb version to do this. You would just flatten basically the payoff matrix and feed that into MLP, and that do fairly poorly, as one would imagine. And then you can kind of, another slightly improved version of this would be to build in equivariance. So for example, if you were to order all the actions by their average payoff, say, and that version does a bit better, but still fairly poorly. NES is the architecture that Luke proposed initially for CE and CCE. So there are pooling functions that are kind of specialized for that kind of use case that had to be changed, and it's not designed as a general purpose architecture. This one. What do numbers decay? Oh, good question. That's a good point. So just quickly go back to the architecture slides here. So K is the number of blocks. So this is how many sequence of block we stack after this, after the initial action embedding. A would be the number of action-to-action operation. So this step, as I mentioned earlier, this step is optional. So you could imagine the output will just go straight out. But this turned out to be useful for application like Nash equilibrium, where they do need to look at other actions more, as you mentioned. And D is the dimension of the embedding vector. So that's a hyperparameter we can choose, basically, what's the dimensionality of each of the action embedding. So here we kind of see all of these different variants. So for example, for Nash equilibrium solving, not having this action-to-action layer is kind of hurts performance. And also, what we can also observe is that, so here we're showing basically the same data, but now just throughout training. So all the dotted line are the baselines. All the solid lines are different variation of the proposed model. So you don't need to read this. It's pretty hard to read, but basically what we can take from this is that for different tasks, the architecture, the performance is sensitive to different hyperparameters. So for example, for Nash equilibrium, you can see that the performance the curves kind of bunch together, and they're essentially bunched together based on the number of blocks that we have. So basically, the main thing that matters is the number of blocks. Whereas for deviation gain, which is a task that require you to probably remember more of what is present in the original payoff matrix, the embedding size matters more. So that's kind of just depending on the task, what matters more is kind of intuitive in that sense. The other thing point to make is that this architecture is quite parameter efficient. So even the largest version of this is has less than 5 million parameters compared to some of the baselines. And this is again, the performance in general, even with the smaller variants, would be better than the baselines. So the second task, well, the other task we said we were kind of interested in is to do this payoff prediction. So a useful question here is to just come back to this initial motivating example would be, given these the pairwise data that we do have, can we make a reasonable guess on the entries where we are missing these pairwise comparisons? So this would be kind of functionally similar to how ELO was initially conceived, but the question is, can we do better? So here, the way we study that is to study in the case of this game, which is typically used in the ranking literature to study different ranking methods. Here, the game is kind of basically you sample depending on Z. So let's say if Z is just 1, then you're basically sampling a pair of random variables, and then that will basically define that pairwise win rates. And the nice thing about this game is that it does capture some of the strategy cycles in the instances of the game. So here, what we're showing is if we're considering just random variables, which is typically what was used in the literature for ranking, to study different ranking methods. What we can see is that P here is the probability of observing, so it's the proportion of the joint actions that are actually observed. So here, P at 10% would mean that given the full game that is sampled, the model only have access to 10% of the joint actions and their outcomes. And the task would be to make prediction about the rest 90% of the game. So in this regime, you can see that the error is relatively high, and the error would go down as more entries are revealed. So now this is a relatively easy instance because you have just these two variables, two scalar that you need to kind of infer based on samples that you do see. A harder instance would be when these are have more confounding factors. So if these are just eight-dimensional vectors, random vectors. And here, but in both cases, you see NfgTransformer kind of is able to leverage the structure that's present in the game. So for a representation learning technique, this is something that's useful to see. Yeah, Patty?
Yeah, I was wondering like how statistically significant these numbers are. So for example, when z is equal to 1, and let's just say for a p equal to 10%, if your method has a mean square error of, I don't know, 0.001 or something, and the other one has a little over like 0.06, what does that sort of tell us? And also I can see the mean square error increases a lot with z equal to 8, which is understandable. But again, like the difference also increases. So is there something that you can tell us about that?
So each bar here, so the error bar here is basically showing the confidence interval over. So I think during the experiment we basically we draw 32 random games that are basically over which we evaluate these. So these error bar kind of represent how confident we are with the level of error we're achieving. And yes, at with z equals 8. So actually the what you could see is that for a method like xelo, with u and v are just the random variables, xelo is actually performs incredibly well. So in fact, so if I look at the table data in the table, NfgTransformer still does slightly better, but it doesn't basically almost doesn't matter. But part of the point is that the ranking algorithm, have been designed with this game in mind, with a specific version of this game in mind. So that kind of explains why like such good performance can be get in this domain. Whereas if you kind of go beyond the domain for which these methods have been designed for, then the performance will suffer more. So whereas if you leverage learning, basically the tools of machine learning, you can kind of have the model try to figure out structures of the game itself. But so I would also say this is not perhaps a really good side-by-side comparison, because in the sense that the method that we were proposing is a representation learning technique. So in that sense, you do need training data. So whereas the ELO methods and XELO, MELO, they basically have one shot. They basically have like one data to work with. They don't try to generalize across games. So this is not a claim that for ranking this is a better method, but just more of a signal that if there is structure to be learned from the game, then the architecture can do it. Yeah. So then I have one more slide. This is the last slide. It's another pretty complicated slide, but let me try to break it down. So here, basically, the idea for the final experiment in the paper, we're basically trying to say, okay, can we actually inspect the model internally and see what the model is actually doing? So here, the game is an instance, is a sampled instance from Bertrand oligopoly from the Gamut dataset, from the Gamut game suite. And what we are showing, so here in the bottom is the sequence of action embeddings. They're updated iteratively after each block and how they're changing. So these action embeddings are projected through PCA to 2D so that we can just plot them here. And what you can see, first of all, is that the set of action embedding overlap exactly between the two players. So for player 0 and player 1, the up-down triangle, they overlap exactly throughout. And that is by design because this game class, Bertrand oligopoly, is actually a symmetric game. And this comes back to the initial motivation where if you have symmetric players, then they should have the same set of action embeddings, and that plays out here. Even though, like in a payoff, if you were to just stare at it, this wouldn't be obvious that this is symmetric. The other thing we would say is that what is highlighted in red is the Nash equilibrium, which the model also finds, which is basically both sides just play action one, and that have a basically near zero gap. And if you if you look at the sequence of action to play attention, so here the way to read this is every row is the action embedding of that player, and every column is the play that action has participated in. So here you can basically see that towards the end of the sequence, every action embedding is paying all their attention onto the Nash equilibrium strategy of the other player. And that kind of over time stabilizes. And you can actually see that halfway through, you can see that there are actually two other actions that are also kind of competing candidates. And that would be like the column 5 of player 1 and column 8 and row 8 of player 0. So basically, the attention mask of player 0 would attend over the action of player 1. So it's a bit counterintuitive, but basically, if you look at the payoff matrix, it kind of makes sense because those are the other two actions that have relatively high payoff. And the other really nice thing is if you look at player 0, actually, let me. Oh, here we go. So the other nice thing we can kind of infer from this is if you look at this block, which is player 0's block 1 attending over player 2's action, attending over player 1's action, this pattern is actually reflected in the payoff matrix here, and it actually shows that every action is attending to the other player's best response. So here, for example, the first row here, this is all the attention is put onto this action, so column 3, and then the next row, basically if I were to play action 1 for the co-player, for the opponent, it's best to play column 1, which is why this row lights up. And here again, this is slightly better, so that's why this one slightly lights up. And here again, this is the best, yeah, these two are kind of roughly the same. I guess they both roughly light up. So this kind of pattern kind of emerged just through training. And basically at every iteration, they're kind of attending, initially they're attending over what the opponent best response would be to my action. And this kind of sequence resolves and stabilizes over time. Now it's important to say this doesn't always work. So in the paper we have some failure cases of this, but also the model here is kind of simplified version of it so that we can do this kind of visualization. But yeah, again, it's kind of useful to kind of visualize to see that they're doing something that's kind of correspond to intuition too. Okay, so that's all I have in terms of results. So to conclude, basically, we're proposing a principal representation learning technique for NFGs. That is permutation equivariant. It's also general, covers the same principle should work for amplitude general sum. The embedding reflects symmetry and replicas by construction. It's parameter efficient. And there are obviously limitations, as the audience also called out. So to scale, we'll probably need to think about other scaling techniques that also the transformer community will be interested in. But again, the theoretical properties are not limited to this specific version of the proposal. So again, the function f being equivariant, that's something that can be implemented in different ways. The model has been open sourced. There's a collab, you can just run it if you scan the QR code. And if any of you is coming to iClear, I'll be there. I'll be happy to chat. Happy to take questions. Yeah, there's a comment about attention weights could be interpreted as Nash, also equilibrium dynamics. So yeah, that's my guess. But again, in the paper we are showing some failure cases too. So in some games where it actually didn't solve for a good Nash, you see basically that it doesn't manage to settle, doesn't manage to converge. The attention mass doesn't manage to converge. But in other cases, especially when they converge to a mixed Nash, you see the attention mass is also mixed at the end. But they would kind of settle on a mixed Nash. Yeah, but these are, the model are simplified. They only have one attention head and they have no action-to-action attention. So maybe there it wouldn't fail in the same way. But yeah, that's kind of the interpretation that we have now.
Cool. So I'm gonna stop the recording now, if that's okay.
Yeah.